Hello and welcome to C-star algebras from a novice perspective. I am finally back from a quick bout with COVID, and I'm happy to talk about something more positive today, because today we're going to familiarize ourselves with positive elements and explore some of their key properties. So in the last video, we talked about the functional calculus for normal elements in a unital C-star algebra. And this enabled us to define f of n for any continuous function f on the spectrum of n, where n is a normal element. And in particular, if f is the identity function, then f of n is just equal to n. So this functional calculus, of course, it used the Gelfand transform, and then f of n would lie in the C-star algebra generated by n and n star. So then this would become a commutative C-star algebra, and then f would be the inverse of f of n would be the inverse of f under the Gelfand transform. Now, in that video, we also noted that if 0 is part of the spectrum of n, then c naught of n here, or c naught of the spectrum of n, is just equal to all the continuous functions. So if 0 is not part of the spectrum, then this is just the entire set of continuous functions on the spectrum. And if 0 is part of the spectrum of n, then this set here is the ideal of functions vanishing at 0. Now, mind you, we can still define functions that do not vanish at 0 in this case as well. All we have to do is to add some number times the unit to a function that vanishes at 0, and we get a continuous function that does not vanish at 0. So we can still do these things. I just wanted to note in particular that if 0 is part of the spectrum of n, then this is actually just the set of functions that vanish at 0. Now, the continuous functional calculus is of course very powerful, as we shall see in this video, but it only works for normal elements, which is lucky for us because all we're going to discuss today is normal elements. In fact, we're going to discuss positive elements. But first off, what is that? So we think of this in analogs. So in a C-star algebra, one can think of the self-adjoint elements as an analog to the real numbers in the complex plane. So this is a direct analogy. And we saw that this analogy was reinforced by the idea that every self-adjoint element has a real spectrum, which we proved in the last lecture. And we take this idea to define positive elements as the set of self-adjoint elements with a positive spectrum here. So if A is a positive element, then the spectrum of A lies in this set here that we have. And in this case, in particular, we write that A is greater than or equal to 0. And much like how self-adjoint elements are characterized by their spectrum being real, positive elements are characterized by their spectrum being positive. In fact, they are defined in this way. And these positive elements determine an order on the self-adjoint elements of A by just setting that A is less than or equal to B if B minus A is greater than or equal to 0. And as we shall see, positive elements are of great importance in the theory of C-star algebras. In particular, when we start getting to the Gelfand-Naimark Segal construction, we will need to use positive states and stuff like that, or rather pure states when we get to the Gelfand-Naimark theorem. And these pure states are defined in terms of positive elements in some sense. So, some basic properties of these positive elements. And there are actually quite many, which is kind of surprising. But if you take some of the more basic properties of positive numbers in the complex plane, we can actually generalize it quite easily to positive elements in a C-star algebra. And in this lecture, we shall prove the following properties. So first off, we're going to prove that every positive element has a unique positive square root. I forgot to write positive here. And also we're going to prove an analog to the Hahn decomposition of signed measures, and that is that every self-adjoint element can be decomposed as the difference of two positive elements, whose product is 0. And, I don't know if you can say that, maybe you can say that there is some sort of analog to positive functions on the complex plane or something, or positive functions on the real line, something like that, or functions on the real line. You can probably find some sort of analog that is cleaner than this, but basically you have that this statement is true. And then we shall also prove that the sum of positive elements is positive. Now this might seem like a trivial statement, but it's actually not completely easy to prove. But all of these properties that we have here follow from the fact that positive elements are also normal elements, which enables us to use the continuous functional calculus. So let's begin by proving the statements about square roots. And we want to prove that if a is a positive element, then there is a unique positive square root of a in the C-star algebra. And we do this by letting f of x be equal to the square root of x on the spectrum of a. So remember, positive element means that we have positive spectrum, so this function f is actually well defined and continuous on this spectrum. And thus we can define the square root of a as simply f of a through this functional calculus. And this is self-adjoint because f is a real valued function, and the spectrum of the square root of a is equal to f of the spectrum of a. This is what we saw in the last lecture as well. And f of the spectrum of a set of positive numbers, well, that is of course a subset of the positive numbers. So thus we have shown that the square root of a is actually positive. And moreover, we use the continuous functional calculus again to prove that the square root of a squared is equal to f followed by squaring, f of a followed by squaring, which is just the identity function on a, which is just a. So we kind of abuse functional calculus, or at least seemingly abuse it, in a very haphazardly fashion, but everything works simply because of the functional calculus. And then finally, suppose that c is another positive square root of a. Then the functional calculus, again, implies that c is equal to f of c squared. But f of c squared is equal to f of a, since c squared is equal to a. And then we have that f of a, well, that's just square root of a. So we're finished. And all of this seems super simple, but it's not trivial if it were not for the fact that a is a positive element and hence normal. And next, let's prove the Hahn decomposition also that I mentioned. So we want to prove that if a is self-adjoint, then there are two elements a plus and a minus here, both greater than or equal to 0, such that a is the difference between these elements, and these elements times one another are 0. Not so easy to prove this, but all we need to do is find two suitable continuous functions, and then we're golden, because remember, here we have that a is a self-adjoint element, so it's normal, so we can use continuous calculus, no problem. So here we set f of x equal to x plus the absolute value of x, and then we take g of x to be minus x plus the absolute value of x, divided by 2. And we just define both functions on the spectrum of a, and we can use continuous functional calculus like nothing. So we note a few things. First off, f and g both are of course positive valued functions due to this term here and this term here. And f times g is a pretty easy exercise, and I leave it to you to verify that f times g is the 0 function. And finally, we note that f minus g is just the identity function. And thus, using the functional calculus, we set a plus equal to f of a, and a minus to be equal to g of a. And then, of course, a is just equal to f of a plus g of a, or f of a minus g of a, because f minus g is the identity function. And then we also see that a plus times a minus is just f of a times g of a, which is f times g of a, which is 0. Really simple stuff when we have the functional calculus. And now for the statement that seemed most trivial but wasn't actually the most trivial to prove. And for this statement that the sum of positive elements is positive, we need the following lemma to characterize the positive elements. So this lemma states that if A is a self-adjoint element, then the following four conditions are equivalent. So first we have that A is greater than or equal to 0, or A is positive. And second condition is that A equals B squared for some self-adjoint B. The third condition states that if C is greater than the norm of A, then C times the unit minus A is less, or when we take the norm of this, then it's less than C. And this is true for every C that has this property here. And then finally we have the fourth condition, which is basically the weaker version of the third condition. So here we have for all, and here we have for some. So the 4 basically trivially follows from the third condition. And as we saw in the last couple of slides, the implication that 1 implies 2 follows trivially from the fact that every positive element has a positive square root. Now let's prove the final part. So basically what we need to prove is that 2 implies 3, and we need to prove that 4 implies 1. So that's what we need to prove now. And first, assuming 2, that is that A is equal to B squared, then of course A is equal to f of B, where f of x is equal to x squared. Once again, we use the continuous functional calculus to our advantage because we assume that B is self-adjoint in our calculations. And as a result from this, we have that the norm of f on the spectrum of B is equal to the norm of A. This is simple by definition. And this implies that f takes values between 0 and the norm of A everywhere on the spectrum of B. And since A is less than or equal to C by assumption, we get that C minus f lies between 0 and C, like that. And now we can just calculate this difference here, or the norm of this difference. And this is actually quite easy using, once again, the functional calculus, because C minus A is just equal to C minus f viewed as a function of B, because C here can be thought of as the constant function. But this is a continuous function, so once again we can use the continuous functional calculus or the Gelfand transform to state that this here has to be equal, or this norm has to be equal to this norm here on the spectrum of B. But C minus f lies between 0 and C, so this norm here is less than or equal to C. So therefore we have that this 2 implies this statement here, which was condition 3, which in turn implies condition 4. And now let us finally assume that 4 holds, or condition 4 holds for a particular C. That's if C is greater than or equal to the norm of A, then this is true here. So we assume that this holds for a particular C, that is, has norm greater than or equal to A. But this, in turn, is equal to this. Once again, we think of C here as the constant function and the identity function here. How is just the identity function applied to A? It's of course A. So C times 1 minus A is just the function C minus the identity function applied to A. And due to the Gelfand transform or the continuous functional calculus, whichever way you want to see this, that is equal to the norm of C minus the identity function on the spectrum of A. But this implies something quite strong, and that is that the identity function is non-negative on the spectrum of A, because if the identity function is not non-negative, then this would have greater norm than C here. So actually, we have that this statement here is equivalent to stating that the spectrum of A is positive. And thus, this condition here, which we have, implies that A is positive, and we're finished. And using this, we can now easily prove that the sum of positive elements is, once again, positive. So say that A plus B is greater than or equal to 0. Then we can use this characterization from the lemma to prove that A plus B is positive as well. So we set C1 to be greater than or equal to the norm of A, and we let C2 be greater than or equal to the norm of B. Then, of course, by the triangle inequality, C1 plus C2 is greater than or equal to the norm of A plus B. And now we can calculate this, because if this expression here has norm less than C1 plus C2, we are done. And this is pretty easy. So we just rearrange this a bit and use the triangle inequality to claim that this is, of course, less than or equal to C1 times the unit minus A plus C2 times the unit minus B. And then once again, due to the fact that we know that A and B are positive, we know that this is less than or equal to C1, and we know that this one is less than or equal to C2. And thus, this sum is less than or equal to C1 plus C2, which we had here. And from this, we see that A plus B must be greater than or equal to 0, or A plus B must be a positive element. Now, we have proven a few statements which are pretty simple to prove just using the functional calculus directly on positive elements. But now the final property that I want to prove for positive elements is a bit more tricky. So if A is an element in a C-star algebra, an arbitrary element that is, then A star times A is positive. So this is quite a big statement. And you know, in operator theory, this is of course a pretty well-known statement, and it's not very hard to prove because then you have that whole machinery. But in this language of C-star algebras at this point, we don't really have these tools to prove this statement. So we need to use the statements we proved earlier in this lecture. And I'm going to warn you right here. This statement is actually a lot trickier to prove than it seems at the surface. And I was first debating whether I would include it in a separate video or not, but then I decided, you know what? It's better to have all of these properties of positive elements in one video, even if the video becomes a bit long in the end. But this is like the perfect moment to just take a little break before embarking on this final big theorem of this lecture. Now, to prove this statement, we need a few things. First off, we need all these previous statements in this lecture. And then we also need this particular ring theoretic fact that the spectrum of A times B and the spectrum of B times A are basically the same thing. They can differ at 0. So one of them can contain 0 and the other one may not. But if we take the spectrum of A times B and add the 0, then that is the same as the spectrum of B times A with an added 0. And this is left as an exercise for the viewer. Now, if you try to do this and you get stuck, just write a comment or like below the video, and I'll give you a hint. But it's really not central to the theme of the video or the theme of positive elements, so I really didn't want to include a proof of this statement in this video, even though it's not completely trivial to prove this. But let's try to prove this theorem assuming that this is true. How does the proof look like? So first off, we need to use some auxiliary notation and prove this thing in a few steps. So first we set B equal to A star times A. And then we see that B is the self-adjoint element, and we can use this Hahn decomposition to write that b is equal to b plus minus b minus, where both of these are positive elements and where their product is equal to 0. So we're going to use all of this. And now we use some more auxiliary notation. So we let c be the positive square root of b minus, which we can do because b minus is positive. And then we set t equal to a times c. Now we note a few things. First, since c is the limit of polynomials in b minus with 0 constant coefficient, we have that c times b plus is equal to 0. And now I just want to note quickly how we see this. So c is a limit of polynomials in b minus. This is because b minus, when you take the square root of that, you have to go to and look in the C-star algebra generated by b minus and its complex conjugate, which is itself. And that is just the limit of polynomials. So by definition, that has every element in that C-star algebra has to be a limit of polynomials in b minus. So that's why c is a limit of polynomials in b minus with 0 constant coefficients as well. And therefore we have that c times b plus is equal to 0. So that's actually an important little detail to note, that c times b plus is equal to 0. And that is because, let's see here, b plus and b minus, do they commute? I think they do, because b here is self-adjoint. Yeah, we can do that. Yeah, b plus and b minus commute, so this is fine as well. So then minus t star times t is equal to minus c a star times a times c, because t is equal to ac here. And then we can just write a star a, which is equal to b, which is equal to this right here. So we get this equality here. And then since c times b plus, or if we really want to be careful here, we can take this c times b plus, and that is equal to 0, of course. So this is just equal to c times b minus times c. But now look at c, it's the positive square root of this. So it commutes with b minus, which means that this is just b minus squared. And thus it's positive because b minus is positive, so minus t star t is positive as well. And we see that the spectrum of this is positive. Now our next phase of the proof involves showing that plus t star times t is also positive. Because once we have that this is positive and we have that this is positive, then we can prove that they have to be 0. So let's do this. And we do this by writing t as the sum of x plus iy, where x and y are the real and imaginary parts of t, which simply means that x is equal to this and y is equal to this. And note in particular that both x and y are self-adjoint elements, because that's going to be important. So then we have that t star t plus t times t star can be expanded in this way. And once you do all the calculations and remember that x and y are self-adjoint, you find that this here expression here is just equal to 2 times x squared plus y squared. And now I'm going to claim that x squared and y squared are both positive number or positive elements. And I leave it as an exercise to prove this statement. Now, if you get stuck, just remember continuous functional calculus, because x and y are self-adjoint elements. And so, as this is a sum of positive elements, we have that it's itself positive. And now, as a result, we have that t times t star, which is equal to this expression here, minus t star t, which is, of course, equal to this plus b squared, because minus t star t is equal to b minus squared. then once again we see that it's a positive element plus a positive element. So t times t star is positive. And now we use this ring theoretic fact that the spectrum of t times t star adjoined with 0 is the same as the spectrum of t star times t adjoined with 0. And this implies that t star times t is also positive. But this leads us to the final part here, where we note that both t star t and minus t star t are positive elements, which implies that the spectrum of this element has to be 0. There is no other way. And since this is a self-adjoint element, its norm equals its spectral radius, and hence we see that b squared is equal to 0. And now, as b is self-adjoint, it follows that b minus is equal to 0. And then we see that b, which is equal to a star times a, which is equal to b plus minus b minus, which is then just equal to b plus, is positive by default because b plus is positive. Now, as a final exercise, you can try to prove that b minus here actually has to be 0 because b minus is self-adjoint. And you can also try to find an example of an element d that is not self-adjoint while still satisfying this equation that d squared is equal to 0. And that's just involves trying to find an example of a C-star algebra and then a non-self-adjoint element satisfying this equality here. It's not that difficult once you try it. So, to recap this lecture, which has mostly been about going over some of the key properties of positive elements, we began by basically noting that positive elements are a generalization of the notion of positive numbers in the complex plane. And they are characterized by having a positive spectrum. And using the continuous functional calculus, we could prove that several familiar properties are true for positive elements, such as the existence of a unique square root. And we used this to prove that every C-star algebra contains many positive elements, since any element of the form a star times a is positive itself. And I'd like to end this lecture on this note and talk a bit about what we're going to do next. So now we have positive elements, and thus we're going to be able to start talking about states and pure states and representations of C-star algebras, which at the end of the day will lead us to our final goal, which is the Gelfand-Naimark theorem, which states that every C-star algebra is in fact an algebra of operators on a Hilbert space. So we're almost there, just a few more lectures. Although I don't know how many more lectures we'll need, I can promise you it's not that much further on until we're finished, which is actually a bit earlier than I expected, to be honest. But yeah, that's it for now. Have fun with the exercises and have a good time until next time. Bye.